Hi, welcome to Fluid Mechanics. Today we're gonna solve this question. Water flow through a horizontal pipe band that exits into the atmosphere, as shown in the figure there. The flow rate is 8.3 the power of 10 the power of -3 meter cube per second. Calculate the force in each of the rods holding the pipe band in positions. Neglect the body forces and viscous effect and shear force in the rods. Thus, the first we need to understand the question, which is calculate the force in each rod holding the pipe. So, what is the force? This force. So this one, we need to name the force as the reaction force. So of course, the flow will be like this. Right? And then there is counter force, we call as a reaction force. And because of this weight, we need to counter this force. This is R, this is Ry, so this is Rx, and this is Ry. Right? So you can see in this figure. So from here, we need to specify the control volume. So this is our control volume. Alright, in the control volume, if we cut across this section, definitely we have the hydrostatic pressure acting in this position. Since this one is exposed to the P atmospheric, thus P here, P at point 2 equal to 0. You can see here. From this case, step number 1 is we need to list out the point 1. What happened at point 1? And as well as point 2. So what happened at point 1? Point 1, do we have the velocity? Definitely have. And do we have the velocity at point 2? Yes. Do we have the pressure? Yes, we have the pressure at 1. Do we have the pressure at 2? Definitely 0. Because exposed to the atmospheric pressure. And then the Z1 here, the Z1 is almost slightly the same with Z2. Alright, this is very small pipe because you can see in millimeter. So we can assume that Z1 almost the same level with Z2. Alright. So from here, we need to find the velocity at each location, velocity 1 and velocity 2. So in order to get the velocity, we need to use the continuity equation. Step number 2, we need to find the velocity based on the continuity equation, which is the volume flow rate, which is Q1 equal to area 1 V1 and Q2 is equal to area 2 V2. Q1 is equal to Q2, and given here that the flow rate is 8.3. Multiply with 10 the power of -3 meter cubic per second. Right? So from here, let's find velocity 1, which is Q1 over area 1. So Q1 is 8.3 multiply with 10 the power of -3 over area 1, which is, when we look at here, our eyes, it is circular shape. So apply the area of formula. Area equal to pi d squared over 4. So pi diameter given here is 75 millimeter. Convert to SI unit become 0.075 squared over 4. Try to simplify using your calculator. You will get the final answer is 1.88 meter per second. Next, we need to find the velocity 2, which is Q2 over A2. Q2 same with Q1, which is 8.3 multiply with 10 to the power of negative 3 over pi. Diameter of the pipe here given 37.5. So convert to SI unit is 0.0375 squared over 4. Simplify. Finally, you will get 7.52 meter per second. So after you find the V1 and V2, you need to apply the energy equation. Okay, step number 3. Apply energy equation, or you can apply Bernoulli equation as well. So energy equation is heat of pump plus V squared over 2G, this is 1, plus P1 over gamma plus Z1 equal to heat of turbine plus P2 squared over 2G plus P2 over gamma plus Z2 plus heat loss. Since this is very short section, we assume that there is no loss. So cancel this out. Since the Z1 almost slightly the same, slightly equal, so we can cancel this one, Z1 and Z2. There is no pump, there is no turbine. Alright. So from here, you can find the pressure. So pressure 1 basically equal to V2 squared minus V1 squared over 2G, and then this gamma as the denominator of pressure, you convert to the other side, multiply with gamma. Right, so V2, what you found previously is 7.52 squared minus V1 is 1.88 over with 2G 9.81 multiply with gamma 9810. Last, you will get pressure 1 is 26.5 kilo Pascal. Alright, so from here, calculate the force in each root. So after you have found the pressure at 1, okay, you use the momentum equation, conservation of momentum. Step number 4, apply momentum equation at, you can say at x axis. So here we say that summation of force x location is equal to mass flow rate multiply with V2 minus V1. This is x, this is x. So look at here, we have the velocity at x. Yes, this V1 is actually V1x. velocity at 2. Do we have velocity 2x? No, we only have v2y. So v2x, we don't have it. We cancel out 0. So summation of force, we need to look at the summation of force in x-axis. So we have force in this component P1A1 and Rx. So P1A1 go to the right, positive. Rx going to the left, negative. So P1A1 is positive minus Rx equal to mass flow rate given here 0 minus V1. V1 in this case is aligned with V1, is the same with V1. V1 earlier we got 1.88. So here P1 is actually this one we got earlier, 26.5 kilopascal multiply with area at point 1, which is pi, diameter is 0.0755 squared over 4 minus Rx equal to mass flow rate. Alright, the mass flow rate is actually equal to rho Q. Rho of water is 1000. The flow rate or volume flow rate here given is 8.3. 8.3 the power of negative 3 multiply with, right? Multiply with negative 1.88. So you simplify the equation above, you will get Rx is finally become 132.6 Newton. How about the Ry? So apply again the momentum equation at y-axis. Okay, apply momentum at y-axis, which is summation of force in y component equal to mass flow rate V2 minus V1. This is y, this is y. So Fy, we look at here. Is there any force in y component? Only Ry. That's it. So Ry is pointing upward. It is positive. Positive Ry equal to mass flow rate multiplied with V2y minus V1y. So do we look at here V2, which is in the y-axis. So we have V2y equal to V2. And do we have V1y? No, we don't have any vertical velocity. So V1y is actually equal to 0. V2y is actually equal to V2. Where is the V2? 7.52. This one, mass flow rate is actually equal to rho Q. Rho of water is 1000. The volume flow rate is 8.3. The power multiply with 10, the power of negative 3, multiply with 7.52. Thus, simplify, we got here is 62.4 Newton. Therefore, that is the final answer.